Morning everyone, I am Shruti Sharma, a research scholar at the Indian Institute of Technology, Bombay, India. Today I am presenting my research work titled as Valorization of Constructed Wetland derived Lignocellulosic Waste for Development of Biomass-based Polymeric Composites. Moving to the need of study, in our day-to-day life we often come across these stockpiles of discarded biomass or waste biomass lying near the countryside, public dump sites or thrown near the water bodies. Currently, worldwide, the common approach to deal with these so-called waste biomass includes open dumping and open burning, which leads to severe ecological concerns, human health risks, and social issues. The extent of damage can be realized by the fact that the global annual generation of these lignocellulosic waste biomass is around 140 gigaton per year, out of which only up to 10 to 12% is put for gainful utilization for secondary purposes. The burgeoning problem of unsustainable management of waste biomass and the resulting ecological and human health issues has been highlighted by many global news articles, and here are few clips of them from different parts of the world. The first one talks about the increased risk of premature death due to air pollution caused by biomass burning. The second one here is related to the increase in biomass burning in Japan and South Korean regions. Here are the few news articles which is related to the open burning of biomass in the regions of national capital of Delhi in India. It is indeed evident that the sustainable management of waste biomass is the need of hour, and efforts for their valorization is the key to achieve the UN's 2030 agenda on sustainable development. Therefore, the present study believes that the challenges associated with the waste biomass management can be addressed by adopting the circular economy and cascading principle approach, which basically emphasizes on the maximization of resource effectiveness by creating the most valuable purposes possible over multiple lifetimes. Due to the physicochemical characteristics of lignocellulosic waste, it has been identified that they can be transformed into potential sustainable raw material for construction products. Such valorization approach will not only minimize the dependence on timber and wood-based products, but it will also help in fulfilling the demands for sustainable construction products. At the same time, they also offers low carbon route for development of construction materials. Beside agro and forestry waste, one of the emerging sources of lignocellulosic waste are the biomass harvested from domestic wastewater treatment facilities based on so-called natural treatment systems. The focus of the present study is on the gainful utilization of waste biomass harvested from constructed wetland post-domestic wastewater treatment. Currently, composting, cattle feed, and heat generation are the typical uses of waste biomass harvested from CW, which offers low value product and lacks market value, and thus they are mostly left discarded. So this is the CW for Reuse Research Station located at IIT Bombay campus. The biomass harvested from here are processed further to derive Cana indica fibers. Based on the compatibility study, a suitable polymeric matrix was chosen, and the two raw materials were mixed together in 7 different mix ratios, and the compounded matrix was fed into the injection molding system, and the Cana indica reinforced polypropylene composites were developed. The developed composites were then subjected to various physicochemical, thermal, mechanical, and structural studies. Moving to the results and discussion, in terms of flexure characteristics, flexure strength and flexure modulus were determined. In the present study, the maximum flexure strength achieved was 47.8 megapascal at 28% of fiber loading. The flexure modulus improved with increase in fiber loading, and the maximum value achieved was 2.25 gigapascal, which is approximately 63% higher than neat polypropylene composites. In terms of impact resistance, which basically describes the capacity of the developed composite to resist shock loads, also was found to be improved with increasing fiber content, and the maximum enhancement was found to be 40% as compared to the neat polypropylene composites. The maximum value attained was 1573 joule per meter square. In terms of tensile properties, tensile strength and tensile modulus were determined. The tensile strength of the CIPP composite exhibited a marginally decreasing trend with a maximum value of 27.6 megapascal. Young's modulus followed the similar trend with that of bending modulus with a maximum value of 3.16 gigapascal, which is approximately 216% higher than neat polypropylene composite. The fracture surface morphology revealed fiber pull-out, fiber debonding, and fiber rupture as the major failure mechanism for the test specimens. In terms of water absorption for 24 hours, the developed composite exhibited much lower value than the engineered wood materials, which is quite advantageous for maintaining the structural integrity of the developed CIPP composites. The density was found to be comparable to the wood counterparts, and it ranged between 0.96 to 1.07 gram per cc. The thermal stability of the CIPP composite was studied using TGDTA. The left side shows the TGA curve for the composite materials, in which the red curve shows the TGA curve for neat polypropylene, which we can see indicates the single stage degradation. Whereas after inclusion of Cana indica fibers, we can see there is a shift in TGA curve for all the 7 mix ratios, with the maximum in case of CI-80PP, which is 88% fiber loaded neat polypropylene matrix. The similar change has also been reflected in case of DTG curve. A maximum of 21-degree rise was observed in case of CI-80PP composite, which indicates its highest thermal stability among the 7 different mix ratios. The crystallographic study was carried out using X-ray diffraction technique. The left-hand side shows the X-ray diffraction spectra corresponding to neat polypropylene composite, whereas the right-hand side shows the X-ray diffraction spectra of 7 different mix ratios. The crystallite size was calculated using the Debye-Serre equation, and it indicated that the fiber addition in amorphous PP caused significant increase in crystallite size. In case of 040 crystal plane, it ranged from 15 to 23%, whereas in case of 110 crystal plane, it ranged from 11 to 19%. And the similar can be observed here. In case of 110 plane, it ranged from 16 to 21.18, whereas in case of 040 crystal plane, it ranged from 18.16 to 21.65. It is worthy mentioning here that the increase in crystallinity of the PP matrix will have a significant impact in improving the thermal stability of the polypropylene matrix, and the similar we have seen in case of thermal stability while we were discussing about it. Coming to the conclusions of the study, discarded biomass from domestic wastewater treatment facility can be potentially used for developing natural fiber reinforced composites. Developed Cana indica waste biomass derived polymeric composites can be potentially used for automotive and architectural interiors in civil infrastructure applications. Such valorization approach reduces environmental burdens occurring due to unregulated disposal and mismanagement of waste biomass. It also offers a promising strategy for waste biomass recycling, aligning with the circular economy and cascading principles approach. It also offers opportunities for startups and entrepreneurship. It is hoped that the present study will potentially contribute to UN's 2030 agenda on sustainable development, along with the various schemes of Government of India, including Atmanirbhar Bharat and Make in India schemes. Thank you to all the participants for listening to my presentation and giving your valuable time. Thank you once again. Thank you.